Hello, students. Uh, have a nice day. Today is a great day, of course. So, today we shall be continuing what we were doing in the previous lecture, that we were calculating the electric potential due to some distribution of charges. So, today we shall be doing the same thing. So, in the previous class, we calculated the electric potential due to a single point charge, and then we calculated the potential due to a dipole at its axial point as well as its equatorial point. So the funny thing is that you got a potential value, a non-zero potential value for an axial point, whereas in at any equatorial point you got that the potential due to a dipole is zero. Okay, this is very interesting and you should remember it because it's maybe it may ask you for a short question type of thing. So I think it's recording. Okay, now today we shall be doing a bit more things, like we are going to calculate electric potential. Today's lecture will be short somehow. Electric potential for a system of charges. For a system of charges, you have been given a system which consists of numerous charges. Okay, they consist of numerous charges. That means you don't exactly know how what is the number of charges in that given system. So first of all, and you have been given a system of charges and you are going to calculate the potential of these charges at any given point. Like if let this point be M, it is a point M, and Q1, Q2, Q3, some random arrangement of charges. Okay, some random arrangement of charges. Q6, so many charges, and you just extend it to Qn. There are n number of charges present around M, and you need to calculate the potential due to Q1 at M, due to Q2 at M, due to Q3 at M, and all of these potential at M. And you have to show that what is the net potential at M. What is the net potential at M? Okay. So I think you get the diagram. We have to make it a little smaller so that we can fit in our statements. So write the statements. We have been given. So the statement is, we have been given a system. We have been given a system of n number of charges. Okay, n number of charges. Number of charges. What are the charges? They are Q1, Q2, Q3, and dot 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 Qn. You can take them as capital Q, so need not worry about the notations. So we have been given a system of n number of charges that has been given to you. We want to calculate the potential due to these charges. Okay, due to these charges at a point M, which is at a distance r1 from Q1, similarly r2 from Q2, and so M is your point. Now you can draw the figure here. M is your point, and this is Q1, this is Q2, this is Q3, this is Q4, and dot 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 Q. and this is those distances. You can draw the distances. Okay, these are the distances. There are many number of charges. There are many charges in between them, between 4 and n. Many charges. Okay, this can be n can be 5. Okay, just write immediate after it. This can be 1,000. This can be 10,000. So we need not worry about that thing, but we need to calculate the collective potential at m due to these charges. So I assume that you have understood the figure up until now. So it is visible from here. So you can name these distances as R1, R2, R3, R4 right now. It is R1, it is R2, it is R3, it is R4, it is Rn. So just let us come to the direct formula. As we know, for a single point charge Q, for a single point charge Q, what is the potential at a distance R? It is given as V equal to 1 upon 4 pi epsilon naught Q by R. This is your general formula. This is your general formula. Now we have to calculate it for Q1 at a distance R1, which is the point M. So let it be V1, since we are denoting it as 1 and its distance is R1. So let that voltage or that potential of Q1 at M be V1. V1 equal to potential of Q1 at M. Okay, you can write like that. So what should be it? It is V1 equal to 1 upon 4 pi epsilon naught Q1 by R1. It is your equation 1. Similarly, you need not write everything. Similarly, you can write V2. Similarly, you can write V2. Similarly, V2 is equal to 1 upon 4 pi epsilon naught Q2 by R2. Similarly, V3 is 1 upon 4 by epsilon naught Q3 by R3. Similarly, Vn is equal to 1 by 4 pi epsilon naught Qn by Rn. It is capital, okay. It is capital. So these are your respective potential, the separate potential. So H we know. So you could have asked me, sir, yesterday you saw that for a negative charge you denote it a negative. So there is no problem with that, because when Q3 is negative, you just mention it here. Okay, you just mention it here. So V3 shall be negative. There is no. So let us calculate the collective potential. As we know that electric potentials are scalar quantity and scalar quantities can be added algebraically. So we are going to add them algebraically. So the net potential at M is V is equal to, what will be that? V1 plus V2 plus V3 plus dot 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 plus V, and this is the collective potential. Now you need to write the formulas of at here, just like 1 upon 4 pi epsilon naught Q1 by R1. Similarly, write for V2 1 upon 4 pi epsilon naught Q2 by R2. Similarly, write for Vn 1 upon 4 pi epsilon naught Qn upon Rn. Okay, so you see that there is some common term you can get out. What is that? It is 1 upon 4 pi epsilon naught. So inside the brackets you can write Q1 by R1 plus Q2 by R2 plus dot 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 plus Qn upon n. This is your formula. This is your formula. Now, in order to make it something compact, so we cannot write if there are 10 charges, we cannot write q1 by r1 plus q2 by r2 plus q3 by r3 and such that to q10 by r10, because it will take a long time. We are going to introduce something new that will make the equation a bit more compact as usual. So V, since it is an addition, so we are going to introduce summation 1 upon 4 pi epsilon naught summation. Okay, summation from n is equal to, so you can write not n is equal to 1 to n qn by r. This is your required equation. This is your required equation. Okay, this is what you need, your required thing. This is your required equation. So when you will be going to calculate these things, you have to make sure that it is given in this format or this format, because in summation for calculating these terms, for there are some general formula, so we can use here. I don't remember if it has been asked like this for a system of charges in any exam till now, but some derivations has been given. So since it is a discrete system, we have used the word or the term summation in this equation. It is a discrete system. We can actually point out q1, point out q2, point out q3, point out q4. We can actually do that since it is a discrete system. But we are more interested in finding the electric potential of a continuous charge system, So in the next few minutes, we shall be considering ourselves in order to derive the electric potential for a continuous charge system or a continuous system of charge. For all this of today up until now, we gathered the information to how to derive the electric potential for a given discrete charge system. Okay, so you actually know what is a discrete charge system. That's why we used summation in the last step of our derivation. Okay, so now we shall be considering how to calculate the, or in order to, in if a given charge system is continuous, like what is that charge system? You have been given a line, you have been given that the line is totally charged with some total charge q. So you have you remember that about linear charge density, about surface charge density, about volume charge density. So we are going to calculate electric potential for those system of charges. So these are quite simple. So you can change the heading. That we are going to calculate the electric potential due to a continuous system. You can also change the heading. So for a continuous charge system, okay, so for a continuous charge system, in this case we shall be considering all of the continuous charge system at once, and like some of the discrete charge system also. We are going to calculate a general formula which will contain everything to calculate the potential of any given system of charges, if that system consists of any continuous charge system or any discrete charge system. So write it like this: electric potential due to continuous charge distributions. distributions. So this may involve you in 1D. So I think in case drying up, I have to use another pen. So if it is a continuous charge system, so let us consider a continuous charge distribution. So it has not been mentioned that what is that distribution. Okay, is it in 1D, is it in 2D, or is it in 3D? So if it was in 1D, so you have been given a linear charge distribution. If it was in two dimension, you have been given a surface charge distribution, and if it is on three dimension, you have been given a volume charge distribution. So we are going to calculate a general formula, that is, let us consider a continuous charge distribution. So that continuous charge, that charge is distributed over some space. Okay, that charge is distributed over some space. So we are going to consider very small amount of charges at specific point. We are going to consider very small amount of charges. We shall be considering. We shall be considering very small amounts, very small amount of charges dq at points. Let those points have position vector Ri. Let M be the point at which we want to calculate the potential. Let this is Ri, okay, not R1, it is Ri. Let R be its position vector. So if R be its position vector, and those points are having position vector Ri with respect to point M. Okay, so we can write that the general formula is, since it is a continuous charge distribution, previously we described about the discrete charge distribution, and now we are going to discuss about continuous charge distribution. In discrete charge distribution, when we used to sum all of them, we used a term summation. In this case, we shall be using the term integration. Okay, we are going to integrate it. So in previous case, v is equal to, you calculated, v is equal to 1 upon 4 pi epsilon naught summation n equal to 1 to n qn upon rn. Okay, qn upon rn. It might be small, so need not worry about it. So if it is a directly, if we know the position vector of M, we can write 1 upon 4 pi epsilon naught summation 1 to n qn by r minus ri vector. Okay, so you can write here I, you can present here I. Okay, it is very compact since it is related to this thing, so we can write r minus ri. Now we shall be converting this summation into an integration. Okay, so we are directly using it. So 1 upon 4 pi epsilon naught, the constant term gets out. In case of summation, you write integration and you write dq by r minus ri. This is what your formula is. dq by r minus ri. This is the small amount of charge. Okay, dq by r minus ri. This is your general formula. Now, for a linear charge distribution, for a linear charge distribution. Okay, for a linear charge distribution of linear charge density lambda, linear charge density lambda. Okay, so what is the amount of charge in that? You as well know that dq is equal to lambda dl. dq is equal to lambda dl or lambda dr, you can write, no need to worry about that. So lambda is equal to dq is equal to lambda dl. So in this case we are going to replace this dq by this term. Now for a linear charge distribution, and going with that we are going to calculate the electric potential at point M due to a surface charge distribution also. For that, I hope you remember that for a surface charge distribution, we use sigma. We use a sigma. So for a linear charge distribution, it is lambda, and for a surface charge distribution, it is sigma. And we are going to use, I just let it be gamma. Okay. So we are going to replace this thing in the previous equation. Not now, we are going to do that a bit later after I have mentioned all the surface charge distribution and volume charge distribution also. So you are going to replace this thing by this. Now for surface charge distribution, okay, I am not writing this much, I am writing dq in case of this is sigma ds. Okay, and for volume charge distribution, let me write a bit better. Distribution for volume charge distribution. Okay, for volume charge distribution, then dq is rho dv. Oh, I remember now, it is rho dv. So we are going to calculate each thing. Okay, for linear charge distribution, let that potential be VL for denoting L or denoting length. And for surface charge distribution, let that potential be Vs denoting surface. And for volume charge distribution, let that potential be Vv for which denotes the volume charge distribution. Why we are doing all these things? Because we all just consider that system consists of all these things, like the line charge distribution, the surface charge distribution, and the volume charge distribution as well. So total net potential be VL plus Vs plus Vb. So 1 upon 4 pi epsilon naught sigma of integration of L. What is dq for line charge distribution? Lambda dl by r minus ri. Similarly, 1 upon 4 pi epsilon naught sigma ds by r minus ri. Similarly, for volume charge distribution, it is 1 upon 4 pi epsilon naught rho dv by r minus ri. So this is your required formula. So if as at a certain space you have been given some linear charge distribution as well as surface charge distribution as well as volume charge distribution, you can actually use that formula. Now if any of them is absent, like surface charge distribution is absent, you term this point 0. If volume charge distribution is absent, you term this term 0. So you are left with this system only. So it is a general formula, the general formula. But if, let me bring some twist to it, that what if some discrete charges are also present in there? Some discrete charges are also present in there. So you can write V as if at last if some discrete charges are also there. Discrete charges are also present. Some discrete charges are also present. So you could have calculated the potential at point M due to these discrete charges earlier, and you can just add them separately. So V is equal to VL plus Vs plus Vb plus Vd. This is Vd is the potential due to this discrete system of charges. So for today, I'm just ending this lecture at this point. And if you have any doubts, you can actually ask in the comment section. And I have given my contact details. If you have any problem regarding numericals, you can actually ask me there. So this is your last step. It consists of VL, VS, VB and VD. VD is the discrete potential. VD is the potential due to the discrete distribution of charges. Okay. So in a space, these are the possible things that can be present. In they may be absent. If they are absent, you can actually omit this thing from this equation. If it is absent, you can omit this thing from the equation. So there is no need to worry. Okay. So up until then, take care, practice numericals, and like our videos, and subscribe to our channel. Share to your friends also. So thank you. We'll see you soon.